Good morning, everyone. My name is Rahul Tavva, Senior Network Cloud Infrastructure Engineer at Kairos Technologies based out of Dallas, Texas. Over the past decade, I have led large-scale transformations for the global enterprises, including migrating more than 2,000 plus sites to SD-WAN, and modernizing manufacturing networks, and implementing AI-driven routing architectures. Today's session is about building next generation network infrastructure using Rust, a language that has fundamentally changed how we approach safety, performance, and concurrency in production networks. We'll explore how Rust enables zero trust packet processing, AI based routing decisions, and enterprise grade security without compromising on the performance. So, we'll break down the session into five parts. Why Rust for the network infrastructures, real time, real world case studies, practical implementation techniques, security, enterprise adoptions, and key takeaways and the next steps. The challenge of modern network infrastructure. The problem is pretty clear these days. Our networks are growing faster and more complex than our tools. We are moving from 10 Gbps pipes to 400 Gbps backbones with sub millisecond latency requirements for high frequency trading, 5G core functions, and real time analytics. Routing decisions are no longer static. They are being driven by ML models that need real time interference, optimizing for latency, congestion jitter, and even energy efficiencies. Meanwhile, in the legacy stack in such as C and C++ carry decades of technical debt and security baggage. Buffer overflows, dangling pointers, raise conditions that attackers love to exploit. And the operational cost of patching and hardening these systems is growing substantially higher. In short, the gap between what the network needs to do and what our current tools allow is widening to a large extent. Why Rust is ideal for network infrastructures? Rust solves this problem without forcing us to compromise the ownership model. Memory safety is enforced to compile time without a garbage collector. No runtime overheads, no pauses, and no leaks. This matters in the networks where dropping a packet is not an option. Zero cost abstractions. Write code that looks high level but compiles down to machine code as efficient as a handwritten code. We can design expressive APIs for packet parsing without adding cycles. Fearless concurrency. Rust makes it safe to share state between threads without locks, enabling parallel packet processing without the race conditions, which is a really great memory safety. By eliminating buffer flows and use after free, Rust removes the root cause of 70% of CVEs in network software over the last decade. In production, this means you can hit line rate performance while guaranteeing safety properties that were once though impossible in the system language. Zero copy packet processing with Rust. In traditional stack, a single packet might be copied 5 times. NIC to kernel, user and kernel to user space, and the kernel back to the NIC. Each copy adds a latency and burns CPU cycles. At 400 Gbps, even a single extra copy can cost millions of hardware over time. With Rust, we can eliminate most of it. Map NIC buffers directly into user space with safety abstractions. Pass references instead of making memory copies. Use borrow checking to guarantee no dangling pointers or double freeze. Integrate with async runtime like Tokio for non-blocking packets I/O. In our tests, moving from traditional copying to Rust zero copy approach reduced packet processing latency by 40 to 65% and freed CPU cores for additional workloads like telemetry analysis. Let's do a case study. We're taking the financial services industry. So the routing in the financial service industry, this was for a major US exchange with extreme latency sensitivity. Security, which is one of the most important. 94% of the vulnerabilities disappeared overnight simply because Rust made them unrepresentable in code. No more emergency midnight patches for the buffer overflows. Latency. Routing decisions dropped from 120 milliseconds to 32 milliseconds. That's nearly 4 times improvement in the HFT. That can be the difference between winning and losing a trade. Throughput. Same hardware, 3.4 more transactions per second, no extra network cards, no extra CPUs. AI-driven routing in Rust. With Rust, we can run ML reference directly in the forward path. No round trips to separate analytical engine. Data collection. Telemetry at tens of thousands of samples per second using zero cost abstraction. Model training. Offline or historical routing data with features like utilization, jitter, packet, and drops. Interference. Rust-based engines run these models in microseconds, selecting optimal paths in real time. Hot swapping. Swap out models without stopping traffic, enabling adaptive learning network techniques. This makes it possible to have truly self-optimized network with decisions are dynamic as the traffic itself. Practical Rust techniques for network programming. These are the three powerful techniques stand out. Efficient protocol serialization. Using for compact zero copy serialization, deserialization of the routing headers, and telemetry data. Custom allocators. Pre-allocate buffers with predictable latency at 400 Gbps in nanosecond matters. Ring buffers. Lock-free packet queues with atomic index for deterministic throughput. These patterns let us match and often beat the performance of hand-optimized code while keeping Rust strong safety guaranteed intact. Security advantages of Rust. The majority of the network CVEs come from memory safety issues, exactly what Rust eliminates. No buffer overflows, no use of after free, no data race. Strong type system prevents logic errors in packet parsing and routing state machines. Even when we do need unsafe blocks for hardware access, Rust forces us to isolate, encapsulate, and audit that code. This drastically reduces the attack surface while keeping performance at a bare metal levels. Let's do a case study of a manufacturing network resilience in a manufacturing industry. A Fortune 500 manufacturer has had a recurring nightmare in the production lines halted by the network outages, and then the recovery time was up to 17 minutes. Gradual performance degradation from memory leaks was also a major issue. After implementing the routing, the manufacturer hit the uptime of 99.998%, and the failover and recovery dropped under 200 milliseconds. Security patches applied without taking the network offline via hot patching, and the VP of operation told the Rust and error handling turned our network from a frequent failure point into our most reliable system. Enterprise adoption strategies. So you don't have to rewrite everything on one day. It basically starts by targeting the bottlenecks where safety and performance improvements will have the biggest ROI. Use FFI bridges to integrate Rust models with CC++ legacy systems. Run parallel deployments to validate Rust performance under production loads. Use Rust testing framework for unit integration and property-based testing before rollouts. Phased deployment. Start with non-critical paths, then migrate to the core routing functions. This approach minimizes risk while steadily replacing fragile legacy code. Key takeaways. Rust lets us achieve safety without sacrificing the speed. Zero copy processing and fearless concurrency means fewer CPUs, low latency, and higher throughput. Rust deterministic performance makes it AI ready, enabling in path ML interference for the smart route. Thank you for the opportunity and have a great day.